Hello, everyone, and welcome to today's webinar, Smart Chart webinar series focused on FTIR and Raman. My name is Rena Samsu, marketing at EAG Laboratories, a Eurofins company. Before we get started, I'd like to go over a few housekeeping items for today's event. All attendees have been muted. However, we'd still love to hear from you during today's presentation. You will have the opportunity to submit text questions to today's presenter by typing your questions into the questions panel located in the bottom right of your screen. You may send in your questions at any time during the presentation. Wensheng Tang, Manager of Organic Analytical Services at EAG Laboratories, will be answering some of the questions during the presentation, and we'll also collect these and address them during the Q&A session at the end of today's presentation. At the end of the webinar, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us to improve our future events. I would now like to introduce our presenter, Janika Schneider, Senior Scientist at EAG Laboratories.
Hi, Rena. Thank you so much. Welcome, everybody. So my name is Janika Schneider. I have been at EAG for about 8 years. I have more than 10 years of experience in materials characterization. I specialize in FTIR and XRF spectroscopies, and I also manage a variety of projects that involve multiple techniques, such as failure analysis, investigations, and deformulations. Very happy to be here today with you. And here's a little outline of our talk. So we'll start with an introduction to EAG. Then we'll talk about our smart chart. We'll follow with the fundamentals of FTIR and Raman spectroscopies. We'll talk about principles of operations, give some real-world examples, discuss the strengths and limitations of each technique, and also go over the complementary techniques. So a little bit about EAG. We're a global scientific services company with over 600 employees, many of whom have PhDs, and 20 laboratory locations all over the world. What's specifically related to Raman and FTIR, those are done at our laboratories in California, as well as in Missouri and in Eindhoven. So what is the SMART chart? So SMART chart is our acronym for spectroscopy, spectroscopy, microscopy, analytical tool, and resolution tool. And essentially, it is a way to compare the spot size with the detection limit. I wonder if you could see my laser pointer. Here we go. So the analytical spot size versus the detection limit. And here we go from atomic percent down to parts per trillion. And here our spot size varies from angstroms down to microns. So here, the blue techniques are those that provide elemental information, whereas the red techniques provide molecular information. In addition, outside of this chart are imaging techniques that don't really have a detection limit, as well as some bulk techniques that are not really, don't have a spot size. So where does FTIR and Raman fit in here? So they're both molecular techniques, so they're depicted in red. And you can see Raman has a smaller spot size than FTIR. In addition, we're getting information about atomic percent. In some cases, we can go down to parts per million, but in general, it's really atomic percent information. Another thing that's important to consider, in addition to the spot size and the detection limit, is the depth of analysis. This is really important when comparing data from a variety of different techniques. So for example, TOF-SIMS is an incredibly surface-sensitive technique, while compared to FTIR, which probes more of a bulk material. So it's important to know this information to make sense of the results. Okay, so let's look specifically at vibrational spectroscopy. Essentially, the way this works is we irradiate the samples with light, and we cause molecular bonds to vibrate. in the sample. So let's look at a CH bond. It can have symmetric stretching, it can also have asymmetric stretching, and these different modes would actually give rise to a different peak that we would observe in our spectra. And one thing that's important to note is infrared is much more sensitive to changes in dipole moments, so more of the asymmetric type of stretching, while Raman is more sensitive to changes in polarizability, which is more symmetric stretching. And this produces different results. Another thing to note is that the frequency of the vibration is a function of the atom and the bond strength. Let's take a closer look at FTIR spectroscopy. Again, let's locate it on our chart. So again, it's right here. We could see that our depth of our sensitivity is in the percent level, and our spot size varies from millimeters down to about 100 microns. FTIR is the best technique for identifying unknown organic material. We'll explain that in a little bit. So again, how does this work? We irradiate the sample with broadband infrared radiation. That causes the molecules to start vibrating in the excited state. And then we measure this absorption spectrum. You can think of the absorption spectrum as simply a fingerprint of the material. And so all organic compounds have unique FTIR fingerprints. And this is how we can use this information to identify and determine the composition of a material. So let's take a look at a specific example. So here we have an FTIR spectrum of a polymer, a copolymer material, ABS and acrylic. Here we have the percent transmission, and here we have the wave numbers. And notice the convention with FTIR is to have the wave numbers in decreasing order, starting around 4,000 for the mid-IR range, going all the way down to 500. So what do we see here? We see a series of peaks, right? And each peak corresponds to some sort of a functional group, some sort of a vibration that we've excited. So for example, peaks around 3,000 correspond to aromatic bonds, versus peaks around 2,900 correspond to hydrocarbons. Now, in this particular polymer, we have acrylonitrile moiety, which gives a strong peak around 2,200. This is the carbon-nitrogen triple bond. In addition, we have a strong ester peak, which is right here at 1,700. We have an ether peak at 1,200. And then again, we see a strong aromatic peak. What's really important to note here is FTIR is not just, you can't just look at a single peak to understand the structure. You really want to look at a collection of peaks, because certain vibrations, certain functional groups can have multiple vibrations. And so to understand the structure of the material, you want to be able to look at the spectrum as a whole, as a composite. So what are some applications of FTIR? Again, this is an ideal technique for characterizing unknown compounds due to the presence of huge libraries of organic compounds. For example, we have a library of 350,000 compounds, which makes it fairly straightforward to identify unknowns if they are a good match with the library. So any kind of organic material and also some inorganic materials are IR active, meaning that they will absorb in infrared and give a nice spectrum. So contamination analysis is an important area, looking at extracts or outgas species or residues, defects. Also, evaluating the cleanliness of a medical device is a really nice application, where we can extract the surface of that device with a solvent, and then we can weigh out that solvent using non-volatile residue analysis, and then finally characterize the extract with FTIR, and we can compare the cleanliness of different devices. So these are sort of the typical applications, looking at unknowns, looking at changes in the molecular structure due to process. But there are some special applications. For example, polymer cure. a sort of a niche FTIR application that can be very useful, and we'll talk about that later in the presentation. In addition, quantification of oxygen and hydrogen in silicon wafers can be done with FTIR, as well as quantification of hydrogen in the form of SiH or NH in silicon nitride wafers. FTIR can be done in several modes. So the typical mode is the transmission mode, which provides bulk properties. We also have the attenuated total reflectance mode and the grazing angle ATR mode as well, GA-ATR. In addition, we can do all these things with a microscope. So again, the transmission measurement takes place where we have our sample here, we irradiate it with the IR light, and we detect the signal in transmission mode through the thickness of the sample. Again, with ATR, we come in direct contact with the sample with our crystal. So here we're getting information about the top micron of the sample. And now we have recently, in addition, we have the grazing incidence, which is a much more surface sensitive way of doing ATR that gives information about the top 10 nanometers of the sample. This is a pretty new technology. And finally, you can also do reflection mode FTIR, especially if you have a microscope, and that provides information about any materials that can be reflected off of the surface. This is very nice. For example, analyzing contaminants on a gold piece. You don't actually have to do anything. You don't have to transfer the sample. You can just look at it right directly and use the reflection to determine the composition. So again, the big advantage of FTIR is that there isn't a need for extensive sample prep. You can essentially just take the sample, let's say, put it on a substrate and analyze it directly. You could also do liquids and gases using special cells, and FTIR spectra of gases are very sharp, very precise. There's also a KBR method and a Nudrel method for preparing samples. In addition, as I mentioned, you can look at surfaces directly with the ATR and the GA-ATR crystals. So, as I mentioned earlier, if you're not doing the surface analysis or the reflection analysis, you need to move the sample to a transmissive substrate because you need to be able to transmit light through. So generally we do that. We have a tool, we'll take a little bit of the sample, put it on our substrate, and transmit light through. So some of the limitations, we can't really do things that are smaller than 15 microns. Our spot size for FTIR, micro FTIR, is about 100 by 100 microns. We don't necessarily have to fill up the entire spot size, but if we fill up less than 10% of it, we're not going to get a very good spectrum. And the limitation in terms of film thickness is roughly 10 nanometers with the grazing instant ATR. So this allows us to look at thin films that normally would be difficult to do by ATR. So now I'd like to discuss a couple of case studies to show you how FTIR can be useful in solving different problems. So first, we'll look at a contamination analysis of two different haze materials. Next, we'll look at failure analysis of a polycarbonate part that's cracking. And finally, we'll end with a quick example on how to determine cure using FTIR. Okay, so here's the first example, and this is very typical of the kinds of samples that we get at EAG, which is, I have a contaminant on a haze, and you can kind of clearly see it. It has this off color. So the question is, what is this contaminant? And so when we obtain a spectrum, we clearly see a series of peaks, and these peaks generally correspond to silicon-oxygen vibrations. Again, one of the things that we consider is the location of the peak positions, as well as peak intensities. So here, these particular peaks correspond to SiO vibrations. And in fact, when we compare to a silicone reference, we get a perfect match, right? And so now we can say that this particular haze is probably due to some sort of a silicone material. And again, you don't always get perfect match in terms of intensity, but what we're looking at is the combination of peaks and peak positions, and here this is quite a good match. So let's look at a different haze. Here we sort of see the picture. It has a different morphology to it, and the spectrum looks quite different as well. And what we see is a very strong carbonyl vibration right here. And then we have some CH bonding as well. And so again, when we compare this to our library, we see a nice match with a phthalate material. And phthalate is a common plasticizer. And again, looking at the nice match between all of the peaks confirms the structure. And phthalates have a strong ester bonding in them. Okay. So now let's talk about the cracking of polycarbonate. So this is a kind of similar to a lot of failure investigation projects we get where we have a plastic part that has some sort of a defect. So here, the defect is this crack that's developed. When we look at the FTIR spectrum of a good part that doesn't have a crack, we see a fairly good match with the reference spectrum. Okay? Now, when we look at a bad part, now we sort of see a formation of a new peak. So that tells us something else is going on. Something is wrong with this part, right? So when we try to understand, why is this peak being formed and what's going on, we actually took a closer look at the part. Sorry. And we noticed that there was a white residue present on the surface of the part. So we took this residue and we compared it to our libraries, and we found that it seemed like a decent match with a hindered amine, which looks like this. So our theory is that this hindered amine caused basically the decomposition of the polymer and essentially started chewing away at the polymer, which gave rise to the peak that we see right here, which we think is due to the formation of nitrogen bonds in the polycarbonate. So one thing that I should mention is that FTIR will not always be able to provide you the specific chemical structure of the material. It's better for providing classes of materials, such as, okay, this is a group of amines, for example, or this is esters or oils or so on. So in order to determine the exact structure, we did a little bit more work where we took this white residue and we dissolved it and we did mass spec on it. And it turned out the results correlated quite well with FTIR, and we did discover the specific cyclohexylamine. And it turned out this was actually a cutting fluid that was used in the facility. And once they eliminated this cutting fluid, they didn't have any more cracks in their polycarbonate. So this just kind of shows how different techniques can be complementary one another. Okay, so my last example for FTIR is an epoxy example. So this is a chemical structure of epoxy. And when epoxy is cross-linked, typically with a hardener, which is often amine-based, there's a transformation in the structure. And the transformation is where the oxyrane ring that's shown here is changed into an alcohol group, right? Simple transformation. And actually, this is something that we can easily monitor by FTIR because there is a peak for this oxyrane ring, which is around 917 or 911 in that range. And so what you could do is you can measure the intensity of this peak versus any other peak like at 1110 or 1249 that's not changing. And then you can essentially determine cure. So and this also works for a variety of different polymers. As long as we can distinguish between the monomeric form and the polymeric form by FTIR, as long as there's a specific band that we can follow, then we can actually quantitatively determine the cure of a sample. Okay, so let me summarize FTIR. The strength of FTIR is that it's capable of identifying unknown organic materials and characterizing changes in known materials. Again, the strength is the library, the extensive library that's available for FTIR, and also the lack of sample prep necessary to do FTIR. In addition, there's no vacuum applied on the samples, which is good for volatile samples, and this is a fairly non-destructive technique, especially when we use it in the ATR or reflection mode. The limitations of this technique are poor sensitivity, so we don't really see we would not be able to detect minor changes in the sample. For example, if we think that there's some sort of a polymer degradation that's happening in a sample, but it's only happening to 1% of the sample, we would not be able to detect it by FTIR. Also, we are limited in terms of the spot size, so we can't really detect features that are smaller than 15 microns. Another issue is, unlike chromatography techniques, where we get separation of different compounds, here we get all the compounds right away. So interpreting complex mixtures of organic compounds can be very challenging. I have analyzed spectra where I've found more than 6 different compounds in a single spectrum, so it can be difficult. And in addition, this is not a quantitative technique without standards. Okay, so now let's move on to Raman spectroscopy. So very similar to FTIR, instead of irradiating with infrared light, we're irradiating with visible light. So that results in a different spot size. So remember from before, the spot size migrated over, and now Raman can give us molecular information from a 1 micron area. So remember, FTIR, our spot size is 100 microns. We can get away with 15, but Raman, our spot size is 1 micron. So much smaller, so much better for small features. So again, same process. We irradiate with light. Here it's a laser source, and in fact, with Raman, we actually have a variety of laser sources that can be used, and the excited electrons, return and emit a photon, and we collect the photons, and that tells us the molecular structure of the sample, just like with FTIR. It's the same kind of fingerprint. So let's take a look at an organic molecule like that phthalate that we talked about earlier, and let's compare an FTIR spectrum of it with a Raman spectrum. So again, with FTIR, we typically show data in percent transmission mode. Here we have wave numbers. The wave numbers are in decreasing order. Now with Raman, it's the opposite, different convention. So here the numbers are increasing order. And here our units are intensity units. So a little bit different, but one thing you can see is sort of a similar kind of pattern, right? So just almost like a pattern flipped upside down. So here we see the difference in terms of what I said earlier, with FTIR being very sensitive to dipoles and Raman being very sensitive to symmetry, right? So let's look at this molecule. So here we have carbonyl, right? Carbon next to an oxygen. So there's a clear dipole here. The electron wants to pull the oxygen wants to pull the electronegativity towards itself. So this is why we see the carbonyl band so strongly in the infrared. But in the Raman spectrum, it's quite weak, right? Because Raman is much more sensitive to the aromatic peaks. The aromatic peaks here, you can see they're just a series of carbon atoms connected together. They have quite a bit of symmetry. And so Raman will be much more sensitive to aromatics rather than carbonyl. But in general, the spectra have a lot of similarities. And oftentimes they provide the same kinds of information. So what is unique about Raman? Of course, we've already mentioned that it can look at smaller features down to 1 micron. But another very particular application of Raman is looking at different allotropes of carbon, such as graphite, diamond, DLC, activated charcoal, and so on. All these compounds would not have an FTIR spectrum, again, due to their lack of a dipole. But in Raman, they have extremely strong spectra, beautiful spectra, and they can be easily differentiated. In addition, Raman can look at the difference between crystalline and amorphous phases of certain materials. It can also measure the lattice stress and strain. So just like with FTIR, we can do liquids and salts. But one very important feature is Raman can see through glass. And this is really important when, let's say we have a particle we want to analyze that's in a vial, and it's incredibly difficult to fish that particle out. Maybe it's really small, but we can kind of see it. So in this case, it would be really great to use Raman because Raman is not affected by the glass. If we tried infrared on that same sample, we would get no spectra because glass absorbs very strongly infrared. So the glass material would basically take away our chance from getting any kind of spectrum of the actual sample. So how do we do Raman? Just like with FTIR, we can look at powders, solids, single crystals, all kinds of materials. We can also look at surfaces, liquids, solutions, and so on. The main difference between Raman and FTIR sampling is that you can essentially look at the sample directly with Raman, so you don't have to move it to any particular substrate. And you should be able to analyze it. In addition, we can look at film thicknesses that are more than about 1/8 of a micron. Now, it is important to mention the substrate for Raman. Pure metals are very nice substrates. Silicon or glass are okay substrates, but carbon-rich substrates make a terrible Raman substrate. We cannot do Raman because because Raman is so sensitive to carbon materials, the carbon signal will dominate and we will not get any information about the sample. So in some cases, it is prudent to transfer the sample to a different substrate for analysis, but in general, we can do Raman directly. And remember, with FTIR, our preferred mode is in transmission, which does require us to transfer the sample to a better substrate for transmission. Okay, so let's look at some case studies. We have a small particle analysis, materials characterization, and then a very nice example of Raman mapping on a pharmaceutical cream. So let's look at this particle. This is about a micron. We have an SEM image of it. It's about a micron, so it's too small for FTIR. And again, using this collection of peaks, we can identify this as polyethylene using Raman spectroscopy. Again, I should note that Raman does have a nice library of about 30,000 compounds, but it's significantly smaller than the FTIR library of 300,000 compounds. So this is where I'd like to show you the different spectra that you get from a variety of carbon allotrope materials. So, for example, graphite has these particular bands versus DLC has this broad band here. And so essentially all the different types of carbon will have different Raman spectra that can be useful to identify them. In addition, looking at the ratio of some of these D and G bands can provide information about the sp3 versus sp2 character of the material, which is very important for some processes. Okay, so let's take a look at a mapping study now. So here, this is a pharmaceutical cream, and it's composed of two different compounds, API number A and API B, right? And you can see that they have pretty distinct Raman spectra. And so what you could do is you can actually map out Here we're looking at 100 by 100 micron square. You can map out the location of A, you can map out the location of B, and then you could put the two together. And you could see exactly where you have high concentrations of either compound. And so, in addition, with Raman, you have the power of a confocal microscope. So you can actually look at a variety of depths. So this is at a 40 micron depth. You can look at a 70 micron depth. And then you could put all that data together and create this cube, right? And so what you could see is the distribution of the two different components in 3D space. Which is pretty amazing. Okay, so let's summarize Raman. So again, Raman is very good for analyzing organic compounds. It also is a little bit stronger than FTIR in terms of inorganic compounds. Inorganic compounds have more well-defined Raman spectra. Again, the big strength is looking at different types of carbon, but we can also measure lattice energy, amorphous to crystalline ratio, and just like FTIR, this is an ambient condition, non-destructive technique with a minimum area of 1 micron. Some limitations should be acknowledged. For example, Raman suffers from what we call fluorescence, which is organic molecules, when excited with Raman light, with visible light, can fluoresce. And that fluorescence can actually basically cover up the entire Raman spectrum. So often what you have to do is you have to do this photo bleaching to kind of remove this little trace organic molecule that's basically making it impossible to determine the structure of the material. So, and some materials will just fluoresce too much and we will not be able to get a Raman spectrum. So fluorescence is an issue, and we don't really know a priori if it's going to affect any sample because, again, a very trace amount of this can really destroy any potential for Raman analysis. The surface sensitivity is certainly material dependent. So if you have a very thin film, it might be challenging to do it by Raman. Again, just like with FTIR, we get all the peaks from all the compounds present. So if we have a complex mixture, the analysis can be challenging. And again, it's not quantitative without standards, although quite a few quantitative measurements are done using standards and using known literature information in our laboratory. And in this case, the success of the technique is really material dependent. Okay, so now I would like to wrap up with an interesting case study looking at using FTIR and Raman on the same exact material. So here we have this green film. We analyze it by FTIR, and what we determine is this is basically it's a styrene butadiene copolymer film. So we're essentially getting the information about the bulk of the polymer. Now, when we do Raman, we get a series of peaks, and we can identify those peaks as a specific dye, right? So looking at the same sample with two different techniques, we get different types of information, right? And the reason for that is because Raman is extremely sensitive to aromatic compounds such as dyes, and so it's going to pick up that first before it gets any information about the polymer. So you can see how using the two techniques together can give us quite a bit of information. So now just a few words about complementary techniques. So again, back to our smart chart. So on the organic side, the complementary techniques to FTIR and Raman are chromatography such as GCMS and LCMS, as well as NMR. With respect to inorganic techniques, the complementary are SEM, EDS, right here, XRF, and XRD. So using those techniques together with FTIR and Raman can really give a lot of information about the structure of the material. So here's kind of our guide at looking at materials with different features, different sizes. And again, this is specifically looking at contaminants, but this can also be, you know, any sample that has gone through a process that you would like to monitor. So if we have a feature that we want to look at that's less than a micron, our best bet is to use TM or Auger. Now, if it's between 1 and 15 microns, then we can do Raman combined with EDS. If it's more than 15 microns, we should really do FTIR first, again, because of its library, because it doesn't have the issues with fluorescence and so on. And so between 15 and 250 microns, we'll do EDS with FTIR. But if it's more than half a millimeter, XRF is an excellent option to combine with FTIR. You get a lot of good information in this manner. So our expertise at FTIR is looking at complex mixtures, trying to get as much information from this fingerprint, this sort of puzzle that we get, and trying to understand all the various components in it. This is rather tricky and takes a lot of years of experience. We also build custom libraries for our clients. So for example, in particular with contamination analyses, we have built out libraries of common reagents and plastics and different materials that are used in the library, so that when a defect is generated, we can compare that against our own specific library that we built out. In addition, we have a thorough understanding of the limitations of each technique. And so we can use all that information to give a more complete understanding of the material composition. So why would you choose EAG? There are several reasons, but I think it's important to state upfront that confidentiality is core to our business. We're a global reader for materials testing services with a broad range of instruments and expertise that leave us poised to take on even the most challenging material and engineering issues. Finally, in light of the pandemic that's affecting us all right now, I want to stress that EAG Laboratories is committed to the safety of our staff and clients. Worldwide, we have complied with the latest COVID regulations from state and local governments, as well as the Centers for Disease Control. Currently, all of our locations throughout the world remain open, but we may have limitations in customer visits. As this is a fluid situation, we are operating as a laboratory at reduced capacity. We can also transfer your samples to other locations if needed. We encourage you to discuss your options with our sales representatives.